Now we're going to explore power series a little bit more. In section 11.9, we're going to look at functions and we're going to think about representing them as power series. This section, we're going to focus in on a series that we know quite a bit about, this useful power series that generated from the geometric series. So if we have the power series 1 plus x squared plus x cubed plus x to the fourth, which is the power series from n equals 0 to infinity of x to the n. This is centered at 0, and by geometric series, we do know that this has a radius of convergence of 1 when the absolute value in that common ratio. So this comes right out of geometric series where our r is actually equal to x. That's our common ratio, and our a, our first value, obviously here is 1. And so we're getting that it converges to 1 over 1 minus x as long as the absolute value of x is less than 1. This just comes right out of geometric series from previous sections and just now looking at it with that variable x. So this is a function. So when we're looking at this, this is absolutely a function. It's the function 1 over 1 minus x. We can look at that rational function. We're going to do that here in just a second in Desmos. We can look at that rational function. It has a vertical asymptote at 1. And it turns out that this is equal to that polynomial 1 plus x squared plus x cubed, as long as x is less than 1. So if we think about that and we actually go over and let's take a look. If we go over and we're going to go into Desmos and we're going to look at this little image of Desmos, we're going to head over there and take a look at what this looks like as we continue to add. So we're going to actually look at polynomials. We're going to start with looking at the polynomial 1. We'll call that y1. We're going to look at, actually let's call that y0. We're going to look at y1 where we have 1 plus x. We're going to look at y2. 1 plus x squared, that quadratic. So we look at a constant. And we're going to notice when we do that, y3, 1 plus x squared plus x cubed, the cubic, y to the fourth power polynomial, 1 plus x squared plus x cubed plus x to the fourth. And we're going to build these up. Actually, I think I have it set that we can go all the way out to even up to the 50th polynomial. We can look at the 50th partial sum here of the polynomials, and we can see how closely that will actually model this on the interval from -1 to 1. Because remember, we have the restriction that x has to be less than 1. So that's what we're going to do. I just wanted to write that out over here before we head over to the Desmos model and we take a look at what's happening. But we're going to look at how these polynomials actually begin to model 1 over 1 minus x. They start to represent 1 over 1 minus x, which is actually a function. This is a function. Okay, so we're going to take a look at that. So let's go over to Desmos and see what happens. So here we are in Desmos, and here is that actual, I'm going to minimize the screen so it's all in the recording here. There we go. So notice that this is, if we were to zoom out, this is in black, the function 1 over 1 minus x. There it is with its vertical asymptote right at 1. And we're going to look at in red, as I'm graphing here, we're going to look at what happens when I'm going to zoom in again though, because right now we're looking at it from about -7 to +10, and we have to focus in on just -1 to 1, because that's where this polynomial, these polynomials are going to actually model, they're going to fit this polynomial. That's where they will converge to, this power series will converge to this exact function. And we're going to see it graphically here in just a second. So in red, what you're going to see in red is the partial sums. Notice the b on the top of the sum right here. This b is going to increase. We're going to increase it out to 50. So each time it goes up, we're going to be looking at one of those polynomials that we wrote out on the notebook just a second ago. So let me get in here and let's zoom in again here on, there we go. I think that's probably a little bit better. Zoom in from -1 to 1. So in black again, the function 1 over 1 minus x, which we know that's that rational function, vertical asymptote at 1. And now let's take a look at what happens between -1 and 1 as we increase these, as we increase the partial sums that we're looking at here in this power series. So we'll just go, let's go up 1 here. So if we go to 1, notice what happens. We went from that constant of just 1, y equals 1. Now we're looking at y equals 1 plus x. That's that linear function. And notice that obviously that linear function is a closer match. It's starting to converge to that function, 1 over 1 minus x. And let's go up to 2. Now we're looking at the quadratic, and the quadratic is, just watch that curve. It's starting to hug, the red curve is starting to actually hug that black curve, model that black curve from negative, again, we're only focused from -1 to 1. That's where we know it converges. 4, 5, 6. I'm going to go ahead and play this and we'll watch it happen really quickly. So here it's happening. It's basically exactly on top of the function from 0 to 1. And we're watching it just start to, I know it's hard to see, now we're going backwards. We'll run it one more time in the video here. So we'll let it go out. There it goes. It's modeling that function. It's as we increase, as we continue to add, we're getting more and more convergence to that model, 1 over 1 minus x. Okay, so let's head back. That's just a visual of what we're using. That's the function that we're using. And so check that out in Desmos, and we're able to see that matching of those partial sums in the polynomials out to 50 actually on that one, and you see it get very, very close. All right, so let's head back, and now that we're working with that function, that's the function that we want to work with, 1 over 1 minus x. I'm going to zoom in here so that we have larger text. And what we want to do now is we actually want to take that guy, that power series, x to the n, which we know models 1 over 1 minus x, and we're just going to manipulate it and use it to derive a handful of other power series for some other functions. Okay? So the functions we're going to look at are going to be pretty specific. They're going to be tied or able to be connected in some way to that original one. So for instance, this particular one that we're looking at here. So let's take a look at this guy. We've got 1 over 1 plus x cubed, and we want to write this as a power series. So a couple things on the instructions. Use a known series. So our known series, right now we actually only know one series, and we're going to build up a whole bank of known series, but for now the only known series that we know is 1 over 1 minus x. So when I'm writing up, let's maybe come over here and start making a little bank of known series. It's kind of like useful integrals. When we were working in the integration section, we had a whole table full of useful integrals that we proved or came out of differentiation formulas, and now we're going to have a whole set of known series. So we know that 1 over 1 minus x is equal to the power series x to the n, and I'm even going to write that out from n equals 0 to infinity. We know that to be true 1 plus x squared plus x cubed. We know that is true for the absolute value of x less than 1. And another way to say that, and I'll put it underneath, another way to say that is that the radius of convergence is 1, and the interval of convergence is from -1 to +1. So right now that is our only known series, and within this section we might add one more known series as we work through this section, but in the next section we're going to add a bunch more known series. But right now that's the one we're working with. So if we're working with that known series and we come across an example and we want to look at this example, 1 over 1 plus x cubed, and we want to find a power series representation for it. So we want a power series representation and the associated radius of convergence. Okay? So we want to know just also what is the power series representation, and then on what interval or what is the radius in which it converges. So let's do this. So for our example, so how would we do this using a known series? So for our first example, we're going to take the power series. I'm going to zoom in a little bit here. We're going to take the power series. Well, actually, let's start with what we're looking for. So we're trying to take f of x equals 1 over 1 plus x cubed. And we're trying to write that as a power series using what we already knew. And that we want to write this as a power series. So I'll put a little question mark here. And it's known convergence. So what are we going to do here? Well, it looks an awful lot like the power series that I just looked at. In fact, if I were to just say 1 over 1 minus a negative x cubed, we're almost exactly like our known series. I'm just going to scroll over so we can just visualize that known series. So there's that known series, 1 over 1 minus x. Well, basically, I just replaced the x in that series with a negative x cubed. And so all I need to do to write this as a power series is to replace from n equals 0 to infinity, to replace that x with a negative x cubed in the power series expansion to the nth. And then I can just manipulate it a little bit. When I did this, I would also need to make a statement here and say this is true as long as in absolute value, remember whatever x was had to be less than 1. And we've replaced x with a negative x cubed. So that means that negative x cubed must also be less than 1. And we'll follow that through as we do our simplification. This is going to be negative 1 to the nth and x to the 3n. We're still starting at 0 to infinity. And this, as we continue to expand, that when I take that absolute value, of course, the absolute value of negative 1 is positive 1. This becomes just x cubed is less than 1. Take the cube root, and x has to also be less than 1. So this is true when the absolute value of x is less than 1. And another way to state that is that the radius of convergence is 1. If I were to actually write this out, if I wanted to see what these first few terms actually look like, then I could just start plugging in values here. So this is going to be positive 1, and then it's going to be negative x cubed, positive x to the 6th, negative x to the 9th, and so forth. And I have my power series expansion there. So I can say here that this particular function, f of x, 1 over 1 plus x cubed, is exactly equal to the power series from n equals 0 to infinity of negative 1 to the nth, x to the 3n, when the absolute value of x is less than 1, or the radius of convergence equals 1. And that is just using the power series that I started with, 1 over 1 minus x, knowing that that was equal to the power series x to the n, and doing a little bit of manipulation. Okay, let's do another one. Let's build off of this one that we just did, and let's do our second example, and I'm going to leave it on the screen here for a second because we're going to utilize it. Let's do a second example. Let's take g of x, and let's take 3x to the 5th. What if I had 3x to the 5th over 1 plus x cubed? Okay. And notice, and we want to write that as a power series. So again, let's write that as a power series in a known and whatever the radius of convergence. We'll also find the radius of convergence. So notice that that is almost exactly 1 over 1 plus x cubed. All it has with it is a multiplication of 3x to the 5th. And if we just think about what that does, we're just multiplying. If you had a polynomial, which we know that this 1 over 1 plus x cubed can be represented as a polynomial, that's what that infinite series is, an infinite polynomial. And if you multiply a polynomial by 3x to the 5th, you would just distribute that to each term. So we can do that same thing with the power series. So we're going to just come in here and say, I'll leave that up on the screen so we see what that expansion is. So what we're going to say here is just, oh, okay, well, 3x to the 5th over 1 plus x cubed, that's exactly the same as 3x to the 5th over 1 minus a negative x cubed, which we already dealt with that. 3x to the 5th times 1 over 1 minus a negative x cubed. We already took care of that. And so what we can say here is, well, that's just the same as taking the power series from n equals 0 to infinity of 3x to the 5th times, and I'm not going to go through that whole thing again. We're just going to go in here, negative 1 to the nth, x to the 3n. Okay? And then we can just simplify a little bit further, because we could say, well, that's just, if we wanted to, we could say that's just equal to n from n equals 0 to infinity. We'll leave the 3 times negative 1 to the nth times x to the 3n plus 5, powers of exponents. Add the two exponents together on the x's. And if we wanted to write that out, if we wanted to say, well, what would that be if we were to write that out? That would be equal to, expanding that all the way out, we'd end up with 3x to the 5th. For when n is equal to 0, we'd have 3x to the 5th minus 3x squared plus All right, guys, just 1 second. I noticed I made a little mistake right there as I was doing the powers there. So we should have 3x to the 5th minus 3x to the, not the second, I think I wrote second, 3x to the 8th. I was doing the subtraction instead of an addition there, plus 3x to the, then when we're up to the second power, 3x to the 11th minus ... and we would continue on. And so if you just zoom out and we think about the expansion that we had right above here, where we had 1 minus x cubed plus x to the 6th plus x to the 9th, if we think about just multiplying that right here, if we think about multiplying that through by a 3x to the 5th, polynomial distribution here, just distributing the 3x to the 5th to each of those, notice what we get. We get exactly what I have down below right here if I were to distribute that to each of those terms. So think about distributing that to each of those terms there, and you would get the expansion that we have down below here that we just did with the power series. So we're just working with polynomials, infinite though they are power series, they are acting just as they do when they act as polynomials. Okay, so let's come back in here, and the last thing we have to do here is just discuss what the radius of convergence is going to be, where this is going to actually converge. And notice that we didn't actually make another substitution into the power series or the radius of convergence into the interval. All we did here was we just distributed that 3x to the 5th. So it's not going to change where we converge. So we're going to still say that this is true when the absolute value of x, utilizing what we have from the previous example, when the absolute value of x is less than 1. If we hadn't had that previous example and we had been working from here, then we would have the additional step of saying that this is still, and we had just already done this work in the previous example, so I'm skipping that step. This is still as long as what we're substituting in for x here, negative x cubed, is less than 1, and of course that gives me back that that's when x is less than 1. Okay, so note from number 1. We already did that portion. Okay. All right. So therefore, the function that we're looking at, g of x, 3x to the 5th over 1 plus x cubed, is actually equal to the power series of 3 times negative 1 to the nth, x to the 3n plus 5 from n equals 0 to infinity, as long as the absolute value of x is less than 1. All right, let's do just one more example on this video, and then we can come back and do one other piece from this section, because it turns out we can do this algebraic manipulation that we're working with here, but we can even do some manipulation with calculus, and so we'll do that on the other video. But I did want to just start off, I think we can do this example quickly. So let's do this guy. Let's say we had h of x equals 1 over 5 plus x squared. And so notice on this one we can do very, very similar to how we did the previous ones. We're just going to manipulate a little bit. Again, we're thinking about, trying to, my kind of thought bubble here is connecting this to that 1 over 1 minus x, which we know has that power series expansion, x to the n, as long as the absolute value of x is less than 1. So that's what I'm working with. That's kind of going on in my head. Like, how do I make this function look like that? And so how would I do it here? Well, I would pull out a 1/5, and I'd have 1 over 1 plus x squared over 5. And then I'd say, oh, I need that minus. So I'd come in here and I'd say, well, this is the same as minus a subtracting a negative x squared over 5. And so that's where I start, and I go, oh, perfect. So that must be equal to the power series from n equals 0 to infinity of negative x squared over 5 to the nth, as long as, I have to always have this little statement right here, this is important, as long as that quantity that I'm replacing x with, that negative x squared over 5 in absolute value, is less than 1. Okay. Again, just kind of referencing my little thought bubble right there. That's what I'm working with. And then I can just come in here and say, okay, let's just simplify this a little bit. This is from n equals 0 to infinity, negative 1 to the n, x to the 2n over 5 to the n. And this is true as long as, I'm going to simplify this guy a little bit in red here. This will be true as long as when we take the absolute value, obviously that becomes just the absolute value of x squared over 5 is less than 1, which means x squared must be less than 5, or x must be less than the square root of 5. So this will be true when the absolute value of x is less than the square root of 5, which tells me that my radius of convergence is the square root of 5. Okay? So there's my work to manipulate this function and determine its radius of convergence. If I were to expand that out just real quick, just to go back to what does this actually look like. So if I were to write this out, if I were to write out a couple of terms right here, we would have, so when we've got 0, we would be at 1, and then we would have minus x squared over 5 plus x to the 4th over 25 minus x to the 6th over 125 plus dot, dot, dot. So that's what this expansion looks like. I just wanted to mention that we are looking at just, sometimes we can get a little bit lost in the power series, but we are looking at these infinite polynomials when we're looking at these. That's what we're talking about, and its radius of convergence is going to be root 5. And so we could say, therefore, this function, therefore, h of x 1 over 5 plus x squared is actually equal to this power series. It can be represented, this particular function can be represented by a power series from n equals 0 to infinity of negative 1 to the nth x to the 2n over 5n when the absolute value of x is less than the square root of 5. Or another way to state that is that the radius of convergence is the square root of 5. And there we go. All right, so just to motivate our next sections, how would we look at something like this? So our next example that we're going to look at is going to be, how do we write, let's call it g of x. How do we take g of x 1 over the quantity 1 minus x squared? How would we do this one? And so again, remember, thinking back to our little thought bubble up here, how do I connect this guy? So going back to that thought bubble, how do I connect 1 over 1 minus x quantity squared? So the square is not just on the x, it's on the entire denominator. How do I connect that to that power series that we know has the expansion x to the n, that power series x to the n? How do I connect it to that? And that is going to be our next section. And that's where we're going to think about derivatives and integrals. Not our next section, our next video, the end of this section. Okay? So we can also use derivatives and integrals. And that's where we're headed. Okay.